Hello everyone and welcome to this video where we will talk now about the Hermitian and anti-hermitian operators. We will also talk about the eigenvalues of the Hermitian operators. We'll talk also about the product of two anti-hermitian operators that commutative between them, and we will conclude this video solving these two simple exercises to show that these operators are Hermitian. Thank you for watching this video, and I'm asking you to put like in this, share with your friends, subscribing our channel. If you're remembering, on the next video we defined the conjugate operators, where we represent a operator and then its conjugate operator has a dagger, and these two operators will be we define it as conjugate operator if they satisfy this expression. Which means that these two inner products must be equal, and if these inner products are equal, then we call A dagger and A has conjugate operators. But for now, suppose that usually these conjugate operators are different, usually, or I can say has a general case, they are different. But for now, suppose that A dagger is equal to A. If A dagger is equal to A, then we call A Hermitian operator. This means that if we have here A dagger acting on phi, and here we have psi has equal to phi, and here we have A acting on psi has equal to A acting on phi psi, and here we have also phi I A acting on psi, then we call A Hermitian operator. On the other hand, there are another class of operators that we can classify using the conjugate operator. Suppose that for now A dagger is equal to minus A. This class of operators we call, so we're satisfying this expression, we call anti-hermitian operator. Okay, now it's very important to say that the eigenvalues of n of Hermitian operator are real numbers. Yeah, we can show this using the following case. Suppose now the A operator acting on eigenfunction psi is equal to lambda is equal to lambda psi. And from here we can take, for example, the inner product of I acting on psi here with psi has equal to psi, and here we have, here here we have a dagger, and here we have a acting on psi. And remembering we are talking about Hermitian operator, this means that A is equal to A. And now we have that if A dagger is equal to A, then we have also here A acting on psi, here psi, A psi. And because psi is an eigenvalue of A, then we must have, we can substitute here lambda times psi, and we have here psi has equal, also here we have lambda times psi, and we have here psi lambda times psi. Okay. And also remembering the definition of inner product, this term will be equal to lambda complex conjugate time psi complex conjugate time psi the suppose, okay, on the whole space. We are working on the whole space. And also having, for this expression, we have psi complex conjugate lambda psi d of tau. Okay. For now, lambda complex conjugate is a number, and also lambda is a number. We can take out from the integral, and we get now lambda star here integral of psi d of tau, and also here we have lambda time integral of psi d of tau. And we can take this expression to from the right hand side to the left hand side, and we have now lambda star minus lambda time psi integral of psi star psi d of tau has equal to 0. This expression is different to 0, then this must be equal to 0, so that lambda star is equal to lambda. Okay, we have this as the solution, but for now we can remember here that if you have z written as a plus I times b, then the complex conjugate of z will be equal to a minus I times b, which means that if z is a complex number, and then z star will be every time different from to z. But if we have here for example a number j has a real number a, for example, then the complex conjugate of j will be also every time equal to a. This means that here we are concluding that if we have a has an Hermitian operator, this means that satisfying this expression, then its eigenvalue will be every time real eigenvalues or real numbers. Okay, we can go on now trying to obtain the the product of two anti-hermitian operators that commute between them. Okay. Now we suppose here that a dagger is equal to minus a, and b dagger is equal to minus b, which means that both operators are anti-hermitian. And then we suppose here that a commute with b. This means that this commutator must be equal to 0, if you remember from the previous videos. Okay, this actually means, by definition of the commutator, this means that a times b is equal to b times a. On the other hand, we can now take the product of a by b, and now if we take the conjugate operator of this product, we have now this has equal to b dagger times a dagger. This is any property that we have mentioned on the previous video where we introduced the conjugate operator. And then from here we remembering that b dagger is equal to minus b, and we have here minus b, and on the other hand we have a dagger has equal to minus a, and then we have here minus a dagger. Then minus times minus is equal to plus, and we get only a times, sorry, here is only a. Oh yeah, we have here a b times a, but if you remember here, a times b is equal to b times a. This means that b times a is equal to a times b, and then we get this has equal to a times b. Then this actually means that the product of two anti-hermitian operators is an or is a Hermitian operator. And if we have this product, and if you remember also that the two operators that commute between them has the same eigenfunctions, then we can see from here that the product of these two operators will be an Hermitian operator, and then we can get the product of both operators. We can take the product of eigenvalues of both operators has a real number, and yes, has a real number. Okay, now we go on try to get to show that these two operators here are Hermitian operator. Okay, to show this I will change their color, and we have L has equal to minus I times d over d of x. These exercises are very simple if you watch the previous video where we talked about the conjugate operator. If you didn't watch this, I advise you to watch now and go on watching these to solve these two exercises. M is equal to d squared over d of x squared. Okay, if you have L has equal to minus I times d over d of x, then its conjugate operator will actually be equal to minus I d over d of x dagger. If we can consider now these, we can consider now, for example, we can consider now that we have C has equal to minus I, which is any constant which is any complex or constant operator or a number, and then we can consider also that B is equal to d over d of x, so that if L is equal to C times B, then L dagger will be equal to B dagger times C dagger, as we have showed in the previous video and also in this video. Okay, then here this means that we have here d over d of x dagger times minus I dagger, and we have showed that on the previous video that the conjugate operator of a number is equal to the complex conjugate of the number, and then here we have only minus I complex conjugate, which is equal to I. On the other hand, we have showed on the previous video that the conjugate operator of d over d of x is equal to minus d over d of x, and then we have now L dagger has equal to minus d over d of x times I, so that we can write this, because I is a number, then we can write this as minus I times d over d of x. As we can see now, L dagger is equal to L, which is this one. Okay, we go on. We have now m has d square over d of x square, and we want obtain the m dagger. From here we must remember also that we have mentioned on the previous videos that if we have m has equal to d, sorry, I will use here n has a general operator, the differential operator. If you have n has d power n over d of x power n, then n dagger will be every time equal to minus 1 power n times d power n over d of x power n, so that we can see here that for us n, for our exercise n is equal to 2, so that with n equal to 2 we have now m dagger has equal to minus 1 power 2 d power 2 over d of x square, and now minus 1 square is equal to 1 times d square over d of x square is equal to d square over d time d of x square, and then we can see that this is actually 2m. On the other hand, we can show this if we consider that m has equal to d square over d of x square, it's equal to d over d of x times d over oh sorry, it's not true. Then thank you for watching this video. I hope that you like this, so I'm asking you to put like in this video, share with your friends, subscribe in our channel, and see you on the next video. Bye.